The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so today our goal is to discuss some concepts in this question of kind of population or ecosystem level stability, resilience, and associated sudden transitions in populations. All right, stability. And something about diversity of populations. We will revisit this question of diversity more on the last class, where we're going to discuss some of these ideas from the neutral theory in ecology, but it'll be a bit of a preview today. So what we're going to do is we're going to start by just considering the dynamics of just a single population, right, where you have maybe one population that's growing either logistically or via some cooperative kind of dynamic. Right, so kind of single population. And in particular, we're going to try to understand something about this idea of either logistic growth as compared to something we call the alley effect, whereby the population has some cooperative type dynamic. Right, so this is maybe logistic versus the alley effect, and try to understand how this alley effect can lead to the sudden transitions that you read about in the review. Okay. Then we'll say something about the lotka-volterra competition model. All right, so this is a slightly different model from the lotka-volterra predator-prey model that you guys have, or that we've all been thinking about over the last week or so. But it's again kind of the simplest model that you might write down that captures this idea of interactions between species, in particular competitive interactions. Then at the end, and depending on how much time we have, we'll either finish it or not. We'll talk about some of these non-transitive interactions. The so-called rock, paper, scissors, R, P, and S type interactions, and some of the measurements that have been made both in male mating strategies in lizards in the California mountains, as well as kind of a rock, paper, scissors type dynamic that was explored experimentally by Benjamin Kerr in the context of bacterial toxin production or chemical warfare between bacteria. And this subject does come in a bit into this question of spatial structure and how spatial structure may help facilitate the stability of populations. Right? So there's this idea that non-transitive interactions, where you have rock, paper, scissor type interactions, may facilitate coexistence of either genotypes or species. But in some of these studies, there's an argument that that sometimes this non-transitive interaction may not be enough, but then in the presence of spatial structure, maybe it does help. On Thursday, the primary topic of the class will be trying to understand the dynamics of populations when they're spatially extended. Right? So this will transition naturally into the subject on Thursday. Okay. Are there any questions about where we are here or kind of administrative type issues? Okay. All right, so I just want to make sure that we're first all on the same page when we talk about logistic growth. All right, so we can think about, well, what are the simplest ways that we might consider the dynamics, the population dynamics of just a single population? Okay. Well, the logistic growth is kind of maybe the simplest model you might write down that where the population is at least bounded. Okay. And I might even maybe I'll even just first draw exponential growth just so that we can. The very simplest thing you might do is you might just say that n dot might be equal to some r times n. Okay. In this case, if we plotted gamma, the per capita rate of population growth, this is just some line at r. Okay. And in this case, the population grows exponentially. Right? And that means that if you plot, say, the number as a function of time, well, it doesn't matter where you start. You always go to infinity. Right? Now, we can compare this to the logistic growth case, where we just assume that at low density, indeed, we grow exponentially at this rate r, but then we have a linear decrease in this per capita rate of growth as a function of density. All right, so we might write this as, okay, nr. Something looks like this, in which case, if we write this per capita growth rate of the population as a function of the population size, it starts out at r, but then it goes to 0. And indeed, you might even, if you'd like, you could say that it goes down to negative values. So in that case, you could start at population sizes above the carrying capacity k, and you would still come back down here. Right? One of the things that we want to make sure we understand is what the bifurcation kind of structure of these equations is going to look like. In particular, we can think about what happens if we add some sort of death rate to the population. Okay. All right, now, in this case, a death rate, what it corresponds to is something. All right, this is the, OK, we're looking at the bifurcation diagram. What we're going to do is we're going to think about what happens if you look at the size of the population. In this, in the bifurcation diagram, what we typically do is we look at the fixed points, okay, right, the fixed points in n as a function of some external parameter. And here we might just think about delta here, which is some death rate. Okay. The simplest way to include this here would be to have a minus delta n. Right, so the idea is that there's this population. It grows exponentially at small sizes. As the population size grows, it might run out of nutrients or so, and that limits its overall population size. Right? Then we can add another term here, which is corresponding to something about the quality of the environment. So this could be the amount of hunting that is taking place, or it could be a reflection of pollutants in the environment or so. Right? And what we want to do is try to make sure we understand how the size of the population will respond to some death rate. Okay? Now, well, maybe we will go ahead and do a verbal vote. Okay, so in this, in the review that you guys read, this was talking about these early warning indicators in the context of sudden transitions in populations. Okay? So this was saying that whether you're looking at a population or an ecosystem, or maybe even other complex systems such as climate regime shifts, epileptic seizures, and so forth, the authors were arguing that, that in response to a slowly changing environmental knob, the system can experience a sudden transition in the state. Right? Now, the question is here, and those sudden transitions that they were describing, those were fold bifurcations or saddle node bifurcations, right? Where there was a sudden transition in, say, the equilibrium size of the population as a function of some external knob describing the quality of the environment. All right, so the question is whether this population experiences such a fold bifurcation that leads to a sudden transition. All right, do you understand the question? I'll just say fold bifurcation. All right, I'll let you guys vote just so you can use your cards. And this is a fold bifurcation as a function of this delta, which is this death rate. All right, ready? 3, 2, 1. OK, all right, we have a majority now are saying the answer is no. This does not actually have a fold bifurcation. OK, and the reason for that is that we can find the OK, in the absence of a death rate, what is the equilibrium population size? K, right? Indeed, what's going to happen is that as we add this death rate, we can just figure out, OK, well, the fixed points occur when n dot's equal to 0. All these things, there's an n here. We can divide by that. Well, OK, we could just do it just so that we're all on the same page, right? So the fixed point, all right, what we want to do is set n dot equal to 0, right? And that tells us that n times r1 minus n over k minus delta is is equal to 0. Okay. All right, how many fixed points are there going to be in the system? 2. All right, so indeed, and this is n dot. All right, so n equal to 0 is going to be one fixed point. Right. But the other one is going to be when this thing is equal to 0. Right, so then we end up with 1 minus n over k is going to be equal to some delta over r. We can right, so what you can see is that this stable fixed point is going to decrease linearly with this death rate delta. Okay? And it's just going to go smoothly to 0. That's this key feature of this bifurcation diagram. So what happens is that we come down like this. Okay? And indeed, we could even continue this. And the bifurcation occurs here. All right? We want to draw, OK, so this corresponds to a stable fixed point. And a dashed line is unstable. Right. Okay, in this case, this is the stable. And this is the unstable. Right. So this thing here is what's known as a transcritical bifurcation. All right. And it's a bifurcation because the fixed points do something. And in this case, they exchange stability. All right, so what happens is that this thing becomes unstable, whereas the fixed point at n equal to 0 becomes a stable fixed point. Right. So there's no tipping point or sudden transition in this logistic growth as you change the death rate. Right. You can think of it as a situation here where the death rate just kind of starts pulling this thing down. Right. And this bifurcation occurs when you pull it down, when delta is equal to r, right? And in particular, what this means is that if you plot, say, the number as a function of time, right? For low delta, right? Or well, in particular for delta equal to 0, then this is your right. You come to this equilibrium k, right? Whereas as delta increases, eventually you just get to a situation where regardless of where you start, you go extinct. Right. Now, in many cases, we don't draw what happens down here because n being less than 0 is not like a physical thing. But it's useful to think about it mathematically because that's what tells you that was the bifurcation. Okay. Are there any questions about where we are here? Okay. All right. One thing that's valuable in the case of, well, in general, is to kind of switch between the kind of algebraic kind of characterization of the dynamics of the system and the graphical dynamics, because you end up seeing different things depending on how you do it. For the case of the Alley effect, we're just going to look at it and analyze it graphically, just because the equations end up being a little bit cumbersome and I think don't provide very much intuition. Okay. Right. But what you can see is that for the logistic growth, other individuals in the population always decrease kind of your happiness as an individual. So if you imagine that you are some member of this population, then having more members of the population there is always kind of bad for you because it decreases your growth rate. And to think about the happiness of an individual, what you typically want to do is divide by n, because you're thinking about the per capita growth rate. Right? So that's telling you about the ability that you will have to reproduce. Right? So what you would typically do is just then divide by n. And what you can see is that per capita division rate gamma, this is a monotonically decreasing function of the population size. Right? This is saying that more individuals in the population just take up space, resources, mate, something. And so you as kind of an individual never benefit from the presence of other individuals. Okay? Whereas when you have the Alley effect, what that's saying is that over some range of population sizes or densities, there is a positive effect of other individuals in the population. Okay? Alley. this is saying that if we plot gamma, as in particular, the derivative of gamma with respect to n is greater than 0 for some n. Okay. This is just saying that if we plot this per capita division rate as a function of the size of the population, there's some region in which this thing has positive slope. Okay. And often people distinguish between the so-called strong alley effect and the weak alley effect. Right? The strong alley effect corresponds to this situation where at n equal to 0, you start out with negative per capita growth rates. Okay. So this is just some generic curve here that describes this alley effect. The important thing is that it's coming up here at low n. Okay? And what this tells us is that we will have some sort of different dynamics where this is going to be the stable size of the population here. But there's also a minimal size required for survival. So if you start out below this n, then you come down. Okay. All right, so if you want, you could call it some. This could be some k, and this could be n min. Right. This is saying if we plot n as a function of time, starting with different sizes of population, then indeed, this thing is a stable state. But the key thing is that there's this other minimal size required for survival. So if you start out around here, then just above it you come up, but just below it you come down. Okay. So what you see is that this population that experiences the strong alley effect has bistable fates. So it's bistable. And this is bistable depending on the starting size n of the population. Okay. Now, can somebody suggest possible explanations for why there might be an alley effect? Sexual reproduction. All right, and can you explain that a little bit more? That's right. Basically, just the need to find mates. Okay. All right. All right. So this implies that, at some density, sexually reproducing species are expected to have this alley effect. It doesn't mean that the alley effect is super strong at moderate sizes, right? I mean, I think that this statement is true, but it might lead us to conclude that these extreme dynamics that we're talking about here are relevant for every sexually reproducing species. But ultimately, the question is maybe how big is this n min, right? If n min is 2, then it's not a severe constraint on the population, right? Whereas if n min is, if you need to have 100, California condors in order to have a viable population, then that's a problem, right? So I think there really is a quantitative question of kind of how big is this minimal size, right? Other suggestions of why it is you might have an alley effect? Yeah.
If the animal species hunts in groups.
That's right, group hunting. All right, and are you aware of any cases that have group hunting?
Wolves.
That's right. Right. So. That's right. So exactly right. Us, yeah. Right. So wolves, for example, can take down like bison or large animals they would never be able to take down on their own. Right. So this could be wolves. It could be primates. We historically do. I guess we still have some groups. Societies are will have things like this, right? But even at the microscopic realm, if you look at just bacteria or yeast and so forth, there are often cases where food is generated or broken down outside of the cell. All right, so any of these cases where you have secreted enzymatic breakdown. Okay. That was an I. Other thoughts? Yes?
Protection from predators.
Right. Protect. Yeah. And so this is the flip side of this. So this would be predator avoidance, or and an example of that would be what?
Like antelopes.
All right. What do antelopes do?
They run in herds.
That's right. So the standard example here is kind of like is herding behavior of land animals, schooling behavior of fish. Of course, researchers argue about to what degree the benefits are primarily this versus something else. I am not going to weigh in on that debate, but I'd be surprised if this were never true. Right? And all these examples, there's clearly something cooperative about the dynamics, right? And so in that sense, it kind of makes sense to think, oh, there's some element of cooperative growth, whether it's on the hunting side or the protection side. But I want to, all right, so if you look at all these cases, so these would all be very naturally described as some sort of cooperation, right? I do want to highlight, though, that the alley effect can be caused by things that lead to what you might call effective cooperation, right? So it's not like obviously cooperative or not intentionally cooperative, but still has the same effect, right? And a nice example of this is what we call predator satiation. Okay. Can somebody guess what this might mean? Yeah, somebody's laughing, so it's.
If there are enough animals around, the predators will be fed.
That's right. If the predators get full, then you can end up with something that's like this. And the way I think about this is just, in a group like this, if there are, if 20 bears come in and eat 20 of us, then we hope that there are 20 other people that will get eaten first, so that the leftovers can run off, right? So these are the, and this is embodied in that joke that people tell, when they're the two hikers in the woods, and they see, the mother bear that's angry, and one of the hikers reaches down and starts tying his shoelaces, right? And the other, the hiking partner says, oh, why are you tying your shoelaces? You can't outrun a bear, right? And the guy says, well, I know that, but I only have to outrun you, right? Okay, so, that's predator satiation. Okay, so if the predator gets full, then you can get something that looks like this, right? Because below some size, below this n-min size, they all get eaten by that bear, and above it, the population may be able to grow. Okay? All right, so this is, I think, a good example of just, it's an effective form of cooperation. Okay? All right, now, can somebody explain, well, first of all, does this lead to a fold bifurcation if we add a death rate? All right, we're going to think about this for 7 seconds, then we'll vote. All right, the question, so if we add a death rate to this, does that lead to a fold or saddle node bifurcation? All right, I'm going to give you more than 7 seconds because I see a lot of brain activity. Okay. Yeah. All right. Does this one lead to a fold bifurcation? All right, ready? 3, 2, 1. All right. All right, the answer is, in this case, yes. All right. So we'll say alley effect is, in general, the kind of thing that leads to a fold bifurcation. In this case, it definitely does. All right. So it's really very important to be able to take curves like this and to figure out what the bifurcation diagram looks like. Okay? And just remember that the solid and dashed lines here are very useful for getting intuition about what's going on, right? Because stable is telling us that any perturbation away from this point it goes away, right? So we can draw arrows here, right? Arrows come here. And so this is saying that starting at 0, from a differential equation standpoint at least, you can add a single individual, and that individual will reproduce until it gets to the whatever the effective carrying capacity is at that delta, right? Right. So what we can do is we can draw the same bifurcation diagram here, where we look at the population size as a function of the delta. And now it's actually somewhat more interesting looking at, right? Because in the absence of this death rate, we have, it starts at k. But what's going to happen is it's going to come like this. All right. And the reason we call it a fold bifurcation is because these fixed points kind of, they fold over on themselves. Okay? Right. Now this is a bifurcation where, as a function of this control parameter, it's not that these fixed points exchange stability, but rather that the fixed points collide and annihilate. Okay? So in general, a bifurcation is where something qualitative happens to the fixed points. In this case, the number of fixed points did not change as a function of the control parameter, whereas in this case, it does change. Right? But there are only kind of certain characteristic ways in which these fixed points are allowed to change. Okay? Right. So from this, we can draw our arrows. And there's right. N equal to 0 is still a stable point down here, so we can draw. This is where colored chalk would be useful, right? But there's a. Right. We can draw our arrows. All right. What do I do out here? Now, the reason that we say that this population experiences a sudden transition or a tipping point is because you can imagine that this death rate being a slowly changing parameter, right? So you could imagine that it could be a slow acidification of the oceans or a slow increase in the amount of fishing that takes place here. So then what can happen is that the size of the population, it's very healthy here. It's pretty happy. All right, here it's maybe decreasing some, but you might not sound an alarm. But what can happen is that at some critical level of the environmental condition, some critical level of fishing, for example, you can get this catastrophic collapse of the population where over short periods of time, it can suddenly collapse. And indeed, this sort of thing has been observed in a number of fisheries around the world. Right? So if you go to, for example, the Monterey Bay Aquarium in Monterey, California, they have a very nice kind of display explaining kind of how that space ended up becoming an aquarium, because it used to be a sardine fishery and was a very productive fishery in the years leading up to World War II. But if you look at the kind of number of fish that were caught as a function of time, it kind of goes up because they're fishing more and more. But then all of a sudden, they just presumably fished too much. And over just a time span of a few years, the fishery collapsed, and there were just no more sardines to catch. That whole street there used to be canneries. But then it all went out of business, and those buildings were largely unused for many years. But then eventually, the aquarium went and bought some of them and refurbished them, and now it's a beautiful aquarium. So I encourage you to check it out. But that being said, the collapse was probably still bad, right? Even though it led to this nice outcome eventually, right? And what you can see is that not only are these tipping points or the sudden transitions, they can be undesirable in the case of a fishery, but it can also be very difficult to reverse, right? Because it's not that you could have imagined that the bifurcation diagram looked rather different, right? It could have looked like this. All right, what kind of bifurcation is this? All right, so this is still a transcritical, right? It doesn't have to be a line throughout, right? Because in principle, there was this unstable thing down here. Right, so this is, again, n as a function of some parameter, we'll say delta. Right? And so you'd say, oh, well, this is a sort of a rather sudden transition, right? In the sense that a modest change in delta led to a dramatic change in the size of the population. But there's something that's very kind of qualitatively different about these situations, which is that here you can imagine if you improve the quality of the environment, and then you reintroduce fish, or just fish can, or maybe you don't even have to reintroduce the fish, maybe they can come from a different area, then just by improving the quality of the environment, you can get recovery. Okay? Whereas here, that's very difficult to do because the system is hysteretic or has memory. Okay. That means that even if you improve the quality of the environment here, it may be very difficult to get back to your previous state. Right? People think that they've seen this in the context of these transitions in lake ecosystems, so-called eutrophication transition, where you get, as a result of maybe runoff from agricultural uses, you can get these sun transitions, not just of a single population, but of an entire ecosystem. Right? So the lake can go from this thing where it's nice and clear and a beautiful summer vacation spot to this like really green kind of algal takeover kind of thing. Right? And it can be very difficult to get recovery. Right? There was a question? No? Right, so the basic, we'll say something about the early warning indicators. Well, maybe I'll say it now. All right, so based on the review that you read, right, there was this phenomenon of critical slowing down that tells us that in principle, you can anticipate that the transition's about to take place, right? And the statement was that the dominant eigenvalue describing the dynamics of the system went to 0 at one of these points. Right? Okay. Now, the systems they were talking about were presumably systems like this. Right? This is a so-called 0 eigenvalue bifurcation, where the eigenvalue goes to 0 at this point right here. All right, so here's a question for you. Does the eigenvalue describing the dynamics of the system go to 0 at this point? All right. Question. At, oops, no, that's an at transcritical. At a transcritical bifurcation. Do you understand the question? I'll let you think about it for 20 seconds, because this is maybe not totally obvious. All right. Do you need more time? I'm wondering, or maybe people are sufficiently lost or confused. They're not sure what to. All right. Nod if you want more time. No? OK. All right. Ready? 3, 2, 1. All right. So we have, I would say it's a kind of a 50-50 thing. All right. So go ahead and turn to your neighbor and try to figure out, using some combination of math and graphical analysis, whether at this transcritical bifurcation the eigenvalue goes to 0. Okay? All right, sounds like the discussion has gone to completion. Let's go ahead and vote again. All right, the question is, does the dominant eigenvalue of the system go to 0 at this point here, the transcritical bifurcation. All right, ready? 3, 2, 1. All right. It doesn't seem like it's had much of an effect. I see that one person has been convinced of something. I don't know if he's actually convinced or if he was just surrounded and kind of bullied. All right, so what are some different ways of thinking about this? Yes?
Well, one of my neighbors decided to actually just linearize that equation around the fixed point.
All right.
The way, if you were completely unsure of your intuition, this would be a way to check.
Right. Okay, and in general, in life, I'm a big believer when you are confronted with some question, you should first think about it, what you should guess based on whatever intuition might be available to you. And then after you have made a guess based on that intuition, then you go and you do the calculation, which in this case, linearizing around. And where do we linearize around? Around the fixed point. Yeah, and I would say that you really want to linearize, maybe not around. You get the same answer if you linearize around 0. But you really want to, I think conceptually, you want to linearize around this stable fixed point. Right? Because in some ways, it's the stable fixed point that the system is sitting in. And you want to know how is it that you're going to react when you get perturbed away from that fixed point. Right? And you do get the same answer. If but the thing is that it's true that the eigenvalue describing the dynamics around this unstable fixed point also goes to 0. But that's because I think the rules of mathematics somehow say that the fixed points are going to have to do something similar. Right. So I think you do also find that the eigenvalue here goes to 0, but conceptually that's not the eigenvalue that you actually wanted to know about. Do you see how I'm saying that? Okay. Right. Again, the eigenvalue here is going to 0. We can try to explore this a little bit, but I just want to kind of tie this together and say, right, so these kind of local bifurcations that you have maybe heard about, which is this fold bifurcation, the transcritical bifurcation, and also the Hopf bifurcation. Right? So the Hopf is one that looks where you have a stable fixed point that goes and turns into an unstable one, and you get oscillations. So that's where you have something that is going to look like. Though now that I'm drawing this, I'm a little bit. Is there a difference between a Hopf and a pitchfork bifurcation? Okay, yeah. So as drawn, it's either or both, or? Okay. Well, I'll say that this thing also the eigenvalue goes to 0 here. Yeah, because I guess in this kind of you don't have to have oscillations in order to, okay, and it depends on higher dynamic systems, blah, blah, blah. But again, this is another 0 eigenvalue bifurcation. Okay. All right, so the statement is that in principle, you can use this fact that the eigenvalue goes to 0, this thing called critical slowing down, to measure some changes in the dynamics of the system before, in this case, you get collapse, or before, in this case, you get extinction. Okay. The issue maybe is that in this transition, there really is something big that happened at the bifurcation. Right? So you really want to have an early warning signal because there's a dramatic change and it may be difficult to reverse. Whereas here, the population size kind of is smoothly going to 0. And once you get down to your last 2 California condors, you know that you're in trouble. You don't need any sort of fancy early warning indicator based on fluctuations or return time and so forth. Instead, just the number is maybe your best measure for the health of the population. Okay. So I think that maybe I won't do the linearization, but I encourage you to do it because that's what's going to be relevant. In particular, what you want to know is if you linearize around, just to be clear, there's some n equilibrium, right? So you'd say, OK, there's some n equilibrium. And then you want to ask, well, OK, now you want to say, OK, if your n is equal to some n equilibrium plus some epsilon, all right, then if you plug it into the n dot function, you should get an equation that is something where this epsilon dot is going to be equal to something. What should it be equal to?
Lambda times epsilon.
Something times epsilon, right? And what's something?
What we've been calling lambda.
What we've been calling lambda, right? Right. So this is saying that if you go a little bit away from the equilibrium, right? So small epsilon here. That epsilon, the solution to this is an exponential. It's going to get exponential decay, assuming that lambda is what? Negative, right? And that's the definition of this. When we say this is a stable fixed point, this is unstable, that's equivalent to saying that the lambda here is negative and the lambda here is positive. Okay?
Okay, so that's a very easy argument that they exchange stability, and so you know that lambda has to be equal to 0.
Ah, yes. So this is the point, right? That right. So we know that lambda here is positive. Lambda here is negative. Lambda here is positive. These fixed points at this point, they're going to exchange stability. So that means they had to be equal, and where they exchange is when it crosses. I mean, so they both. Well, I guess independently, this went. Well, we should be able to draw this. Although I'm a little bit worried that once I try to draw something, I'm going to get confused. All right, but this is a useful exercise. Right, so in particular, if we plot as a function of delta, we want to, so here we have the lambdas, and we have here this delta. And at delta equal to r, what's going to happen is that we're going to get the one guy is going to go like this. Yeah. OK, I don't want to. OK. Something like that, right? Given that the fixed points went from stable to unstable, unstable to stable, it means they had to cross 0. So if they both cross 0 at that point, they're going to be equal and 0. All right. You guys agree? Yes.
Do we know that the eigenvalues are going to change linearly with the death rate?
No. So in general, they don't. And I'm trying to think if close to the bifurcation, whether I can say. I'm sure the mathematicians I'm sure can say something, but I'm not going to. Yeah.
Does this also mean that whenever we're on a steady state approaching the bifurcation, we'll always see the critical slowing down? If it's a stable fixed point that we're approaching.
Right. So I think that the statement is that in principle, critical slowing down occurs. But that does not mean that you'll necessarily be able to see it, right? Because it could be there's just too much noise or this or that. Yeah.
So something that I was sort of thinking about related to that is, so in this case, it seems like everything about the system, just the fluctuations or anything should be getting very small as you approach that.
Right, so in principle, the fluctuations are supposed to grow. Although this is assuming that the strength of the noise is constant. And in this case, the strength of noise may not be constant because if it's demographic noise and the size of your population is going down, so this is subtle then, I think.
Yeah, okay. I guess the sort of thing is
Yeah, and when we typically talk about these dynamics, we're assuming that there's an added noise source that is independent of the variable. But if it's demographic fluctuations you're talking about, then that won't be true. I think that it's also useful to draw, to get some intuition around this based on this idea of an effective potential. Right? So these are one-dimensional systems, which means you can always write down an effective potential. Right? And in this case, what it's going to look like is, all right, so this is some U effective as a function of the population size. Right? And up here, we have some stable state here, right? That corresponds to something that looks like this. Right? So it starts out maybe at k. What happens is as the death rate increases, this thing kind of turn. Oh, maybe I didn't quite make it. OK. Right. So what you see is that as the death rate here, so as we go down, the death rate's going up. Right. So what happens is that the effective potential describing the dynamics of the population near the equilibrium, it's broadening out. Okay. So you can think about the dynamics as being equivalent to an over-damped particle in an effective potential. Right. So for example, for those of you that have studied single molecule biophysics kinds of things, this could be thought of as a polystyrene bead that's trapped in a laser trap. Right. And as you turn down the power of your laser, then the spring constant describing the dynamics of that bead in the trap, that it gets weaker and weaker. Right? So the potential kind of broadens. And that means that for a fixed kind of injection of noise, fixed temperature, you get these effects where the fluctuations will increase in magnitude, and you get an increase in this autocorrelation time. Right? Because, for example, in the bead in the trap, the autocorrelation time is indeed just equal to the relaxation time of the bead in the trap. Okay? And the bifurcation occurs right at this point here, where you see that this local potential or the local minimum is disappearing. Right? And that's when this stable fixed point is gone. Right? And then you just kind of fall off here. And that's what leads to this collapse, which I have covered up. Yeah, but that leads to the bifurcation. Okay? And you should, for example, be able to draw an effective potential here as well. But I'll let you play with it. Okay. But you can see the location of this unstable fixed point shifting as well. Okay. Although I'm not sure how good my drawing is, because in principle, this unstable fixed point they have to come together. All right, I'm not sure if that's very clear in my drawing, but. Okay. All right, so just to summarize this discussion, I think there are a few ways that you can think of these early warning indicators. And there's a diagram that I like to make that I think makes things more clear, for me at least, which is that if you look at this population as a function of time, right, it goes, and if there's an environment quality as a function of time, right, if the environment has a perturbation, right, then the population will shrink, but then you'll get recovery. And this thing here tells you about the time for recovery. And this basic phenomenon of critical slowing down tells you that as the tipping point approaches, as you approach the bifurcation, the time to recover from this perturbation is going to grow. Of course, the other thing that you can say is that even in the absence of a defined perturbation, even if the environment is constant over time, there could just be the natural noise in the system kind of will fluctuate, just like temperature for the bead in the trap. Right? In principle, then you can measure the size of the fluctuations, the variance, as well as the autocorrelation time, tau, which is for simple systems equal to t, and this also grows as you approach the bifurcation. Right? Yes.
Is it clear that, because I mean the perturbations we've been talking about is I take n and I perturb n to
Yes.
plus epsilon, and then it relaxes to
Yeah.
steady state. Is it equivalent to perturb the environment?
Yeah, right. So it's a good question. What I've been talking about is a situation where you really literally pull in away and then you let go. And that's equivalent for the bead in the trap, that you pull the bead away and then you let go and you watch it come back. Yeah, but the situation in the case of the environment is that if it's a kind of a sudden shift, right, it could be anything. It could be a brief change in, well, it could just be delta, right? So it could be that over some period of time, the death rate increases, or some period of time the growth rate decreases, or it could be that for the perturbations don't have to be bad; they can also be good, right? And you actually get the same. In principle, for small perturbations, it's the same thing, anyways. Yeah. Right. So these are early warning indicators of an impending transition that are based on temporal indicators. And incidentally, one of the things that we've been excited about in my group is actually just trying to measure these things in well-controlled laboratory populations. And so in our case, we're using yeast that are engaging what you might call a group hunting behavior, where they secrete an enzyme that breaks down a sugar, and that kind of leads to this cooperative growth. And at least in that case, we can experimentally measure an increase in all of these things as we approach this bifurcation. The other thing that you might think about is what happens for spatially extended populations. We'll talk more about spatial populations on Thursday, but just while we're here, it's useful to think about it. All right, so instead of thinking about just n as a function of time, now you want to think about density of the population. All right, so one thing that people have talked about is that, OK, but this is now not a, this is not a function of time. This is now a function of position x. Density is a function of position. And this is now environment as a function of position. If you have a uniform environment over position or space, then in principle, you can look at density fluctuations. And this is something that people have talked about. One of the things that we have argued is that there should be a spatial analog to this recovery time. Right, so that corresponds to a situation where you have environment as a function of position. That, for example, you have a sharp boundary or you just a region of poor quality. And in that case, you can look at the density as a function of position, and you get some length scale here. Right? So the statement here is that just because you're in a region of high quality doesn't mean that you're at your equilibrium density, because if you're close to a poor region, right, so if you're close to hunting grounds, then you'll get local depletion of the population. Right? You have to get some distance away from a bad region before you get to your equilibrium. That distance, or recovery length, tells you about the quality of the environment. And it's the quality of the environment at this region, in the good region, where you are. Right? And at least in the laboratory, this is something that's actually much easier to measure than other things, because this is a deterministic phenomenon. Right? You don't have to measure fluctuations over time with a high-quality time series. You don't have to wait for a perturbation in time, like a drought, and look at recovery. Instead, you just take advantage of natural variations in quality of the environment over space, position, and then you measure profiles. We have a collaboration with a professor at the University of Pisa who does field ecology experiments with these algal mats on intertidal communities on islands in the Mediterranean. And we have preliminary evidence that we can measure this in those island communities as well. All right. Are there any questions about this stuff before we switch gears? Yeah.
In that example, how much control do you have over actually assigning a quality to the environment?
Right. So in that manipulation, what they did was they basically go in and so they're like miniature forests somehow, right? So they're little that have alternative stable states. And what they actually do, they go and they like chip away at the rock to remove the things, and they do it over some range so they experimentally basically make it a challenging environment. And apparently they have permission to do this. So don't try that at home without asking the proper authorities. Okay. Any other questions about this? All right. So I think that the nice thing about studying all of these dynamics just for a single population is that it clarifies kind of the essential ingredients in order to get things like sudden transitions. So of course, in natural populations, we have many, many species interacting in lots of complicated ways, but then we'd like to understand those things. But I think since it's so complicated, you kind of feel like, oh, anything can happen, and it's not. You get a little bit discouraged from thinking deeply about it because you just think it's going to be too complicated to try to understand. And so I very much like the idea of trying to really hone your intuition on the simplest possible situation like this, and then bringing that intuition to more complicated or complex situations. Yeah.
I think you partially addressed what I want to ask is whether any of this can be applied to human society.
Oh, yeah, right. So whether this can be applied to human society. It's a good question. People certainly try to. I think, you always have to decide what you mean by apply. I would say that this basic idea that there can be these feedback loops that can lead to sudden transitions in complex systems, I think this is a very robust phenomenon in the sense that I think if you have strong enough interactions, then I think you kind of expect it to be true. Another question is whether you can quantitatively predict when that's going to happen, right? So there was a recent article written in Science or Nature about potential tipping points in human society and kind of global scale things in terms of productivity of crops, and so they have a question mark about they say 2050 question mark collapse, maybe but I would say it's very important to be thinking about these things, and but the question is what to do. Whether, given the uncertainties in your knowledge of where these tipping points might occur, it's always hard to know whether you can make a strong argument saying, oh, we have to stop fishing here because it's going to collapse, or there's always uncertainty in your decision making, right? But certainly in the context of climate regime shifts, people are worried about these sorts of feedback loops and the North Atlantic Oscillation and so forth. And I'm not at all an expert at that, so I don't know whether we should be worried. But it's at least it's good to remember that systems can respond in dramatic ways to small changes, right? And then you have to decide what to do with that knowledge, and I think that's more of a judgment call. Yeah.
In the time example, we had death. It was a death rate. So death and then for space.
OK. All right. So I want to be a little bit maybe more clear. The claim is that, like the delta there that we were thinking about, that didn't have to be the perturbation. It could be, but it didn't have to be. The way that when we're plotting the bifurcation diagram, we're assuming implicitly somehow that there's a separation of timescales, such that this delta might be changing very slowly, and then other things are changing more rapidly, right? So this bifurcation diagram, it's really that you're kind of tracking it, right? So in the context of this n as a function of delta, this thing kind of goes like this, and the idea is that, oh, slowly you're getting more and more agricultural runoff, or the temperature's increasing, or it doesn't have to be human-induced, by the way. It could be something else, right? So the idea is that the population is slowly changing like this, and then eventually maybe you get this collapse, right? Now, a perturbation could be something that it could just be a drought, or this is something that is independent of this delta. But the statement is that over here, now I'm going to be mixing things. This is at low delta, the claim is that you should get a dip and then rapid recovery. As the delta gets bigger, you get maybe even a larger, the same perturbation could in principle lead to a larger dip, right? And then it takes longer to get recovery. And then here, this actually brings up another point, which is that these could all be the same perturbations. All right, so this is a case where delta is increasing as we go down, right? So it could be the same perturbation here. You survive. Here you survive. But then the same perturbation that was survived here could be the same magnitude drought. Just as delta increases, you expect this may be able to push the system past the unstable fixed point because of a loss of resilience. And this is something that we've seen in a variety of different contexts. So I think this is a very general phenomenon, just because the separation here is some measure of the resilience of the population, or the ability of the population to withstand perturbations. What you can see is that the resilience shrinks as we get close to this bifurcation. Did that answer your question? Sort of? Not really. OK. No,
but it answered another question.
It answered another question. OK, oh, good. I'm glad that I answered something. OK, but what was because you're saying, is it the death rate that is causing this perturbation? Or?
Well, no, I was wondering for space.
Oh, OK. Oh, yes, I forgot. Yes, I do remember that you did ask that. Right. So the idea here is that this could just be a region that we fish, and this could be a region that we don't fish, for example. Or it could be that here there's just not as much food for the organism as there are here. So it's just, but the idea is that you would need kind of a sharp boundary between regions of different quality. And that's kind of the situation where you would be able to measure this recovery length. And the basic reason for that is that if the environmental quality is something that changes very slowly, then the population density will just track that, right? And then you can't use that to measure this recovery length, right? And of course, the same statement is true here, right? That if you have environmental perturbations that are changing slowly over time, then that also can complicate this picture. All right, any other questions about that before we move towards multi-species ecosystems? We're going to start with the two species. Yeah, OK. Maybe I'll. All right, so what I want to do is I want to spend the rest of the class talking about lotka-volterra populations, and we're going to move the rock, paper, scissors discussion to Thursday because it's a nice spatial example anyways. All right, so let's think about lotka-volterra. Now, this is the lotka-volterra competition model. All right, so the assumption that we're going to make here is that we have these two species that are going to be interacting, but they're going to interact in the kind of the simplest way that you might imagine, which is that if we plot the derivative of population size n1 as a function of time, we get something that looks like this. Now, the first thing that you want to do when you see something like this is just to make sense of the basic equations, right? In particular, in the absence of the other species, what happens to these populations? All right. What we're going to assume here, maybe for simplicity, is that R1 and R2 are both greater than 0. Yeah. All right, so in the absence of the other species, do these populations survive or not? Ready? 3. We're going to do A, yes, B, no, our typical. All right. Absence of the other species. Right, is ready? 3, 2, 1. Survival. Yeah, they survive. Sure, because I've told you that these guys are greater than 0. What that means is we can think about n1 in the absence of n2. Right? What is this equation? Logistic. Right? Now, if we wanted to think about these as describing competitive interactions, what does that tell us about the sign of the betas? Are the betas greater than 0 or are they less than 0? All right, I'll think about it for 10 seconds. All right. Do you need more time? All right, ready? 3, 2, 1. All right, competitive means that the betas are greater than 0. All right, and what is the assumption somehow that's going into this? Oh, and we should remember that this is minus everything up here, right? Okay. Yeah.
I guess that somehow these two things are there's a fixed amount of some resource that both of these things need.
Okay, right. So there could be some fixed resource,
I mean, it's basically like an effective carrying.
That's right. So it's somehow it's modulating the effective carrying capacity. Right? And how is it that you would describe these betas?
Sort of seems like you'd expect that the beta should be probably less than 1, and maybe not. I don't know. No, I guess it doesn't have to be less than 1, but yeah, how compared to how well an individual of N1 takes up some of this.
Yeah.
This is how much an individual of N2 would take up that same resource.
That's right. Yeah. So I think that's right. And I think there's a question about how explicitly to be thinking about these resources, right? Because it could be that it doesn't have to be one resource, right? This is of course a very phenomenological model, right? It's lumping all the ways in which the species interact into just a single parameter beta. But it's somehow the betas are telling us kind of something about how much does a member of the other species kind of inhibit my growth as compared to a member of my own species, right? Because we have this N1 here, and just this species 1 will naturally lead to a carrying capacity K1 if you only have species 1. Now, the betas are telling you something about how much overlap they have in terms of maybe niche or so, right? Now, if the betas are small, it means that they're not competing with each other very much. Whereas if the betas could be larger than 1. And what that's saying is that a member of this other species is inhibiting my growth more than a member of my own species. Okay. Right. Now, there are right. So the standard way to analyze these equations is to look at these isoclines. Right. So basically, if you say, OK, well, n1 dot is equal to 0, what does that mean? Right. Well, we can just see that that's equivalent to saying that it's n1 plus beta 1, 2, n2 is equal to k1. Right? Right. So this is giving us a relationship between n1 and n2. Right? What do these look like on a plane on n1 versus n2 drawings? Is it a parabola? Is it it's a line, OK? And indeed, we can think about what happens when each of these is equal to one thing or another, right? So if n1, well, maybe if n2 is equal to 0, this thing is going to cross at k1, right? And that makes sense, because this is we already decided that in the absence of n2, this thing is just following logistic growth, where the species 1 will go to k1, right? And that's a stable fixed point, so that n1 dot has to be equal to 0. Well, it's a fixed point, so n1 dot has to be equal to 0, right? And it's going to cross at this other point here, where n2 is going to be some k1 over beta 1, 2. Right? And then we end up with a line. Okay. Now, if we go and we ask what n2 dot is equal to when this is equal to 0, we're going to end up with something that looks very similar, right? But now it's going to be n2 plus beta 2, 1, n1 is equal to k2. Right? This is also going to be a line. Okay? Given what I've said, how many different qualitative outcomes can you get in this model, right? Where we just assume, where we have beta, if we're thinking about competitive interactions, right? Like, how many cases do we need to consider? All right, it's going to be a 0, 1. All right. Do you guys understand what I mean by cases? No? Well, I mean, how many different kind of qualitative outcomes can there be in terms of, species 1 or species 2, winning, or can you get coexistence, or how many different kind of qualitative outcomes can there be? Right. Well, and if you're confused, you can not vote or give me an unhappy face. All right, ready? 3, 2, 1. All right, so we have many E's. All right. And can somebody explain why it is that this is the case without invoking that you've already studied this and you know the answer? Yeah.
So, I mean, if you add another line,
OK,
add it
perfect.
completely on top, under, or it can cross like two.
That's right. That's right. So the next thing I was about to do was draw another line, right? And the reason I stopped is because there are actually kind of 4 different ways in which this other line can be drawn. Okay? And basically, you can have another line that does 1, you can have 2, you can have 3, and you can have 4. Okay? But maybe, okay, these 2 cases, right? So this is, I'll just say 1. Well, okay, I don't know what order. Okay, 2, 3, and 4. Okay, 2 and 3. In both cases, we have a crossing of the lines, right? So maybe does that mean that they're the same outcome, the same qualitative outcome? No. Okay, and what will end up happening here is that we're going to get cases of, let me just, right, so you can get that species 1 dominates independent of starting condition, assuming that both are present at the beginning. Species 2 could dominate. Species 2, they could coexist, or they could, or you get bistability. History dependent, kind of mutual exclusion.
So where is the weighting?
All right, and I just want to draw. So this one here was the we had the dashed line for n1 dot, and we had the solid line for this. Yes.
Where is the weighting of symmetry between n1 and n2? Because to say that I exchange n1 and n2 with dynamics doesn't look like they should change.
Right. Well, so I guess if you swap the labels or so, you're saying. I mean, I guess in the case that if one of them is just above the other one, then then you can distinguish them, right? So if you have a dashed line here and you have a solid line out here, then that means that these are.
But how do I distinguish case 2 from case 3?
Case 2 to case 3.
Because the only thing that's different is that
Well, maybe we should try to figure out which one's which, and then we can kind of figure it out from there, right? Because I think, can somebody remind us what are these lines again? Why are we drawing them, or what did they mean? Yeah, so they're not actually quite a fixed point. We have to be. It's a null line. What's the difference between these things?
For our entire system.
Yeah, right. So the fixed, if we say a fixed point here, what we're saying is that both n1 dot and n2 dot are equal to 0, right? Fixed point means that if you start right there, you'll stay right there. We're not yet saying anything about stability, right? And this is going to be very relevant for Sam's question, right?
so my question incidentally is that the axes are labeled.
The axes are definitely labeled. No, I think I may agree with you, but I'm a little worried that I'm. If you're happy, I'm happy. Well, let's. Right. Okay. Yeah. So right. So a fixed point of this pair of equations would be when both of the derivatives are equal to 0, right? And that's not the lines that we've drawn. Right. The lines that we've drawn are just when one or the other one is equal to 0. Right. So what does that mean about in case 4? Is it possible to have coexistence? No, right? Because there's no fixed point in the middle. But the only case it's possible to get coexistence is either line 2 or line 3, right? But the stability, that tells us there's a fixed point. It doesn't tell us about the stability of the fixed point, though, right? So indeed, what we'll find is that in one case, it's a stable fixed point, you get coexistence. In the other case, it's an unstable fixed point, and you get bistability. All right. What we're going to do now is we're going to ask and try to figure out in which case, how do we label these things? Okay. So what we'll do is ask, first of all, in line 1, we want to figure out, is that a situation where we know it's not going to be coexistence or bistability, but is it going to be a situation where species 1 wins or when species 2 wins? But if you want, you can vote for one of the others. Okay. I don't want to constrain your choices. All right. So it's going to be A is 1 wins, B 2 wins, C not 3 wins. Okay. This is something else. Okay, I'm going to give you. I'm just going to give you a minute to think about what might be going on here. All right. So the question is in situation 1. And I will. Did I? Oh, no, I did that wrong. In this, okay. And for the solid line, this is what we're asking is when n1 is equal to 0. Oh, this is just equal to k2.
Can you add the other null lines? Like
What's that?
the axes? Because there's other null lines, right?
You want more null lines? I feel like there are lots of lines up there already.
The n equals 0 null lines. The axes are actual null lines. Yeah, right.
Oh, yes, that right. Yeah, no, that's true. Yeah.
That
But
helps to, I don't know, I'm confused between labels.
I see.
So maybe, I don't know.
Okay, I'm hesitant to draw anything more up on the board. No, but it is true that that the axes are also null lines, right? Because we have ends up there. All right, I'll give you another 20 seconds to try to figure out this case 1, which of the species is going to win. All right, do you need more time? All right, let's go ahead and vote and see where we are. Ready? 3, 2, 1. All right, so I'd say that there's a slight majority that are agreeing. In this case, it's going to be that 1 is going to win. And I think that it's a little bit hard to figure it out completely. But what I will say is that in the case where we're down here, what this means is that, well, k1 divided by beta 1, 2 is larger than k2, right? Now the question is, well, what happens in the limit of if species 2 does not hurt species 1? Okay. Well, that's when beta 1, 2 goes to 0, right? And that's the situation where this goes up. Okay, so this is saying that if beta 1, 2, and we can figure out where this line is as well, because this thing is k2 divided by beta 2, 1. Right, so if species 2 doesn't hurt species 1, but species 1 really hurts species 2, that's going to be the limit where species 1 is going to win. Right? We are out of time, so I'm not. I think maybe what we'll do is we'll start class on Thursday by. I'll start with this on the board, and then we'll complete this kind of these 4 possibilities to try to get some intuition about it, and also draw these options.